Newberry, and I want to talk to you about one of my favorite things, the Northern Lights. But before I do, let me just tell you a little bit about who is Deb Newberry. Actually, I'm kind of a science nerd, and if you probably ask my children, they will probably confirm indeed that I am a science nerd. In fact, when I was in second grade, I told my parents I wanted to be a scientist, and I was very blessed because they supported me in that ambition my whole life. When I was in college, I actually couldn't decide what I wanted to do, so I focused on 3 scientific disciplines: physics, chemical engineering, and mechanical engineering. I was even a pre-med major for a while. I ended up focusing on nuclear physics, and when I started my employment in the corporate world, I actually started doing thermal and radiation analysis and testing on satellite systems. In fact, at one point there were 12 satellites in space with my stuff on them. Nothing quite as exciting as watching a rocket take off knowing that your stuff is part of the payload. Pretty cool. Now let me tell you about one of my favorite things, the Northern Lights. One of my favorite airplane flights, and I love flying, is the Delta flight that goes from Minneapolis to Amsterdam. Leaves Minneapolis about 3:30 in the afternoon, gets into Amsterdam at 6:30 in the morning, but you're flying during the night. And I always try to sit on the left-hand side of the airplane and look out the window, so hoping I can see the Northern Lights during that nighttime flight. So to talk to you about the Northern Lights, I'm going to turn my whiteboard over so I have a little bit more room to draw pictures. And let me tell you, if you were to ask me, Deb, what causes the Northern Lights? I'd probably say something like, well, it's the ionized particles in the solar wind coming and interacting with the magnetic field around the Earth. And you might go, huh? But let me take it apart piece by piece for you. The first piece that I want to talk to you about is the structure of an atom, which you probably already know, but just in case. An atom has a nucleus or a center core that is composed of neutrons and protons. Those protons are positively charged, and the neutrons, as their name implies, are neutral in charge. So that's the nucleus, the core of the atom. And around that core, we have small, negatively charged electrons that are orbiting or circling around that nucleus. Now, because of the laws of physics, those electrons are only going to exist at certain distances away from the nucleus. Now, normally in a stable atom, you have the same number of electrons with those negative charges as you do protons with the positive charges. So your atom as a whole is electrically neutral. Now, every once in a while, energy will come along and remove an electron from that atom, or perhaps even add in an extra atom or electron to that atom. What happens then is you don't have the same number of positive charges as negative charges, and so your atom becomes unevenly charged. The name of that atom when it happens is an ion. So when I said ions coming from the sun are going to interact with the Earth's magnetic field, you know that I'm talking about an atom that probably doesn't have the same number of electrons as it has protons. It's not charge neutral anymore. So that's part 1. Part 2, let's talk about our sun. Our sun, that energetic mass of hydrogen, helium, nuclear fusion reactions, is a very energetic mass, the star, our parent star. And because it is energetic, it is all the time spewing out those particles that I talked about. Sometimes they're atoms of hydrogen and helium. Sometimes they're pieces of an atom, like individual electrons or protons. And this energetic flow that comes from our sun is called the solar wind. Now, this is nothing like the gentle wind that we may feel on our cheek during the summer, or in Minnesota, the very wintry breeze that we may feel on our cheek in January. This solar wind is actually very energetic, highly ionized particles that are coming from the sun. Now, we've got the solar wind and we've got atoms, and we know what an ion is. Part 3, our Earth. Mother Earth covered with an atmosphere of air, but then the Earth actually has a molten metal core. That molten metal core makes the Earth act like a giant magnet. And a magnet has a north and a south pole. The Earth's magnet has a north and a south pole. So it's almost like that molten metal core creates this giant magnet in the Earth. And it turns out that the north pole of that magnet is very close to the geographical north pole of the Earth. And the south pole similarly is very close to the geographical south pole. So we have a giant magnet in the Earth, and just like the magnets that you probably played with, it creates a magnetic field around the Earth. A lot of times people will laugh at this drawing and they'll say, well, it looks like Mickey Mouse ears, Deb. You're absolutely right. That magnetic field is one of the things that protects us folks here on the surface of the Earth from all of these energetic particles that are coming from the sun. Now, one little thing I want to tell you, that sun and this solar wind, the sun also has its own magnetic field plus the solar wind, and sometimes that's going to cause the Earth's magnetic field to distort a little bit. So you can kind of imagine how these lines that I've drawn as the Mickey Mouse ears on the right-hand side are kind of going to get pushed away because of the sun's magnetic field and also that solar wind. Now, the solar wind from the sun is going to vary with the solar cycle because sometimes that sun is more energetic than it is at other times. So sometimes we're going to get more particles coming at us than at other times. That 11-year solar cycle that you might have heard of. So finally, the very last thing I want to talk to you about is light. What we see. Why do we see colors? Light, the visible light that we see, is part of the electromagnetic spectrum. Big word. But the important thing for you to think about is that light is a wave. So if I draw a wave, we can specify a wave by something called the wavelength. And that is basically the distance between peak to peak or trough to trough on a wave. So what I've drawn here, this distance right here would be the wavelength of that wave that I drew there. Now, the visible light that we see different colors because they are different wavelengths. Blue is a much shorter wavelength than red. We see different colors because they have different wavelengths, and based on the miraculous way our eyes are made, we see different colors when we see different wavelengths. Okay, where do those waves come from? You know what? Let's go way back up here to our atom. These electrons, because of the laws of physics, are going to have different energies. Let's say this is an energy 5. We'll give it just a rating of 5. And this guy is an energy of 3. Down here in this orbit, it has an energy of 3. Here we have an energy of 5. If an electron moves from this orbit down to this orbit, it's going to give off an energy packet of 2. And that energy packet is going to be related to a certain wavelength. So when electrons move up or down or away or onto an atom, they're going to either absorb energy or give off energy. When those atoms go from higher to lower, they're going to give off energy that we can see often as a wavelength that our eyes react to that results in a color. That's why we see the beautiful colors of the northern lights, the greens and sometimes the blues, sometimes the yellows. And the interaction with the magnetic field is why we see them kind of pulsing. If you've ever seen the northern lights, a lot of times it looks like a curtain of light moving across the sky. But it's because of the interaction of those atoms interacting with the Earth's magnetic field, and because of all of those particles coming from the sun interacting with our atmosphere and the magnetic field, those electrons changing energy levels, they change energy levels, they give off energy that we can see as light. So, atoms, that energetic sun that we call our star, the Earth's magnetic field and our atmosphere and the wavelength of light, that's what causes the northern lights. Think about it. So now you know everything you need to know to explain the northern lights to your friends and family and the person standing in front of you at the supermarket. Thank you.